everyone. We have all day talking about grading physics and observations of black hole powered events. Orr is a fellow at CCA and also at Columbia University, and he's an expert at 3D magnetohydrodynamic simulations. We use this method and also analytical method to predict, for example, multi-messenger signals or gravitational wave events and other events as well. So, Orr, please take it away.
Can I just turn off the slides so that
Okay, thank you for having me and thank you for coming. So I'm going to talk about black holes and mass-to-mass transients that are powered by these black holes and how we use numerical simulations to mediate between the black holes and the observations that happen far away from the black hole and learn about the underlying physics of these systems. So let's start with introducing the black hole universe. Perhaps the first black holes come to mind when we think about black holes are these gigantic monsters that reside in the center of galaxies in active galactic nuclei. Now, thanks to EHD, we also have direct electromagnetic observations of this type of black holes. We also have direct sort of observations from another messenger of gravitational waves in LIGO of binary black holes, black hole neutron submergers and double neutron submergers that can ultimately form a black hole. So all of these systems, we already have direct detection or opportunities to look in the eyes of these black holes and study them directly. Other systems that are associated with black holes are supernovae, perhaps the main formation channel of black holes in the universe. However, here, the black holes do not produce detectable messengers. So we have the opaque stellar envelope that doesn't allow us to look into these black holes. So we don't have any way to directly study them. And finally, what I think are the most interesting type of systems that involve black holes are the ones that are yet to be discovered or yet to be detected, the unknown cataclysmic events. One example is fast-blue optical transients, which just recently got their own class thanks to high-cadence optical surveys that showed us that these most luminous optical phenomena in the universe are also accompanied by X-ray counterparts. These X-ray observations tell us that there should be some central engine activity there, most likely a black hole that we know that is associated with these systems. So although we don't know the nature of these systems, we do know that black holes are most likely part of them. So this is the black hole universe, at least most of the black holes that we can think of. And let's connect it now with the type of observations that we can study through them, these black holes. So as you all know, there are 4 types of messengers, the first of which is gravitational waves. So far, we only had detections of inspired gravitational waves. There are 2 classes of gravitational waves. The other type is stochastic gravitational waves. These gravitational waves are coming from sources that emit gravitational waves from different regions at different frequencies. So these are incoherent gravitational waves and therefore much harder to detect. And all the inspired gravitational waves coming from binary mergers that we saw before. So we need 2 binary mergers that are inspiraling, and as they fall into a lower orbit, they emit stronger and stronger gravitational waves. Here we have the chip. Might be better if I close the presentation and reload it, because I see that the movies are getting slower. Is it okay if I do that? Sorry about that. For some reason, I'm not seeing the screen. negative test.
No, maybe just try sharing.
Oh, it's reconnecting now.
Okay.
Yeah, there was a glitch or something.
Okay.
Hope so.
See the west side. You connect. Okay. Something's happening.
Yeah, the Zoom doesn't go. You click on the link,
Oh, okay.
nothing happens.
Nice.
This
Yeah.
can relaunch it. Okay, right. Okay. The other types, let's see, they didn't get better. Okay, we'll have to leave it. It's too expensive. Okay, the other type of messengers are electromagnetic waves. So if we have at least one of these binaries as a neutron star, we expect two types of electromagnetic counterparts. First of which is kilonova from the debris of the merger. This is due to radioactive decay, and the other one is a short gamma ray burst that is coming from the jets that can be launched in the post-merger process. And finally, we have the particle emission. So we have cosmic rays. So if we have this ejecta, the debris of the merger, and the jet that is propagating in the ejecta, we expect a shock, and protons can be scattered back and forth across the shock, and by Fermi acceleration gain energy, reach very high energy, and constitute high energy protons or cosmic rays. And finally, these protons can interact with the photon field in the jet, and through P-gamma interaction, produce pions that ultimately decay to neutrinos and have neutrinos. So this is why these systems are the ultimate multi-messenger sites where we can study all the four types of messengers, or at least this is what is considered to be the case. So in the near future, we will have many opportunities to learn about this type of electromagnetic counterparts and particle emission to gravitational waves. So LIGO is running as we speak, and LIGO is definitely already detected, for binary neutron star mergers, black hole neutron star mergers, and binary black holes. If we're very, very lucky, we may also have some stochastic gravitational wave source, although even if we detect it, it seems to be very difficult to understand that we detected such a source, because the templates are very tricky when we are talking about non-inspired gravitational wave sources. In the electromagnetic front, we have LSST coming in less than a year. LSST is going to transform our understanding in the high energy transient field. It will provide us observations very early on after this type of explosions, and this will open a new opportunity for us to study the early evolution, the relativistic part of explosions such as supernovae, if they include some relativistic components and binary mergers. Ultrasat that will be launched in a couple of years, hopefully, will also provide us similar opportunities through the UV bands. In addition, for the AGN, we have the next generation of EHT that will not only provide us images of these supermassive black holes, but also movies of these supermassive black holes, enabling us to look into the evolution of the vicinity of these black holes and to understand better accretion processes and jet launching and so forth. In the particle emission, we have many types of detectors, from IceCube generation 2, Dune, Grand 10K and 200K, and KM3net, and many others that hopefully will give us some particle emission from these stellar explosions, or maybe also from TDEs or AGMs. So these are very exciting times. All of these facilities will be operative in the next few years, and hopefully the field of multi-messenger astrophysics will get even more exciting than what it is now. So let's start talking about the different types of systems and what we expect from each, and why do we even care about multi-messenger astrophysics. So we will start with, I guess, what we must start with, which is the beginning of multi-messenger astrophysics with gravitational waves, and this is, of course, the first multi-messenger event of neutron star mergers that was detected, GW70817. Probably heard more than you want already about this event. So we'll just look into what we studied from this event. So we had gravitational waves detected for the first time from a non-binary black hole system. And as I mentioned, we expected two types of electromagnetic counterparts, the first of which is this debris from the merger that is ejected from the merger either due to tidal forces or the head-on collision or disk winds from the post-merger system. And this would undergo radioactive decay and power a kilonova emission. And in addition to this, once the compact object that produced in the merger collapses to a black hole, it can launch a relativistic jet, and this jet ultimately can produce a short burst of gamma rays. And this is something that has been considered to originate from neutron star mergers for about 3 decades. And the reason for this is that the typical accretion timescale in the system is supposed to be on order of a second, which is observationally what we see for the duration of short gamma ray bursts. Now, in addition to this, if we consider the interaction between the jet and this ejecta, then once the jet is launched from the compact object, you can see that its interaction with the ejecta, which is what you see here in blue, forms this extended structure that is called a cocoon. And the way it forms is that just like you have a drill bit drilling through the wall, it's shocking ejecta material that is starting to spill sideways and forming this extended structure around the jet. The cocoon co-evolves with the jet, and finally, as the jet is escaping from the ejecta and finally can emit the gamma rays once it's entering the optically thin region, the cocoon can also expand sideways because it's not as relativistic and power emission over a much wider angle, thanks to its high enthalpy or high reservoir of thermal energy. So the cocoon is another important component in addition to the ejecta and the GRB. And indeed, in this event, we predicted that the cocoon will power a bright UV blue emission, but the cocoon turned out to be even more interesting, as this is most likely the origin of the gamma rays that we detected in this event, which were fainter by orders of magnitude compared to typical short GRBs. Now we know that we were not observing this system. We were not in the angle of the jet, so we could not have seen the jet, and the cocoon are most likely the origin for this. However, this cocoon is also the reason why it's less likely to detect particle emission that were considered to come from these jets, and the reason is that we have strong mixing between the jet and the ejecta that suppresses the ability of the jet to form collisionless shocks and efficiently accelerate particles to high energies, and we haven't detected it any neutrinos from this event or from any other event of GRBs, including the brightest of all time that you might have heard of last year. So why do we care about multi-messenger observations? So there are many things that we can do with multi-messenger events. The first of which is that we know that they form black holes. So we can study the physics of black holes as we see them in formation in life. So one thing we can do is to study the neutron star equation of state. The equation of state of dense matter is something we can constrain by the time that it takes the post-merger remnant to collapse to a black hole. The longer it takes, the stiffer the equation of state is. And we can also constrain it from the other direction if we have some deformability measurements from the gravitational waves to how soft it can be, the equation of state. As for the science of black holes, we can constrain the mass of black holes when they form, the spin of the black holes that they form from the angular momentum in the system. We can constrain the kick that the black hole can get from this merger and study these black holes through electromagnetic observations if we understand this system well enough. Needless to say, this was the event that showed us that binary neutron star mergers are playing a very important role in nucleosynthesis of heavy elements in the universe, perhaps the main contributor of heavy elements in the universe. This is thanks to the detection of the kilonova in this event. We had the entire electromagnetic spectrum plus VLBI images detecting these jets. These are the ultimate jet labs to study jets. We had from gamma rays seconds after the merger to radio and X-ray years after the merger. We never had such opportunity to study the properties of relativistic jets, and we could constrain the parameters of jets, of GRBs, as we could never did before. These VLBI images also told us what is the inclination angle of this system with respect to our point of view. And this inclination angle, which is about 20 degrees, could help us constrain the universe expansion rate, because the gravitational wave strain amplitude equation is degenerate between the inclination angle and the strain, and we can, if we know the inclination angle, we can infer the distance. And once we know the distance from the gravitational waves, and we know the redshift from the electromagnetic counterparts, we can constrain the Hubble constant. And we can, of course, conduct a cosmological survey and learn more about the rate of these events, the rate of kilonovae, the rate of short GRBs, and so forth. So there is a lot of fundamental physics that could be studied through these events, and this is what makes them so important and so exciting. And hopefully we will have more of them soon, although so far it doesn't look very promising. So this is sort of motivation, and I would like to draw a comparison to these events through another type of explosions, and these are supernovae. Hopefully we will have the ability to study these events as in much detail as in binary neutron star mergers. So here the physics is very similar, but the system is somewhat different. So we have a collapsing star. This would be sort of the ejecta that we had in a binary merger. We have high angular momentum in some of the massive stars at least. This would be the angular momentum of the binary. And we will have a black hole, which is where most black holes in the universe form. And as this star is running out of fuel and is starting to collapse under its own gravity, it will form an accretion disk. As the gas will hit the centrifugal barrier, it will circularize and form an accretion disk. And this accretion disk will, similar to the case of binary mergers, will launch a relativistic jet. This time, instead of into an expanding ejecta, it will be into a collapsing stellar envelope. So this jet will have to drill its way, just like before, forming this cocoon that you can see here, surrounding the jet. And as they escape from the star, the jet will power this time a long gamma ray burst. Here the accretion timescale is much longer than 1 second. And the cocoon will power its own electromagnetic emission. So you can see that there is a lot in common for these systems. Now, Stan Woosby proposed these systems about 3 decades ago as the progenitor of long gamma ray bursts. But what I would like to show you by drawing this comparison is that they have much more to offer than just progenitors of long gamma ray bursts. So what is the physics we can do with them? So first of all, factory black holes. We can learn about spin, mass, kick of black holes. This is important for many different types of studies that go way beyond collapsars. We can study the origin of heavy elements. In fact, Daniel Siegel and Brian Metzger 4 years ago suggested that collapsars are indeed the main production sites of heavy elements in the universe rather than binary mergers. The reason is that the accretion disks in these systems are more massive. So there is more mass to be enriched and reach high atomic numbers and produce a lot of heavy elements in the universe. However, the question whether these heavy elements indeed are produced sort of consistently and whether they can escape from the star, which is much more massive than the ejecta mergers, is yet to be studied. These are again excellent jet labs. We can do a lot of jet studies through these collapsars. One thing we can do is to try to connect the jet observations with the structure of stars. If you think about it, the jet is a messenger taking information from the black hole, takes it with the jet over 7 orders of magnitude in space and time to the photosphere, emitting this information to us. And the question is if we can use this information to study or learn something about the star that must have something to do with the properties of these jets. Another thing is, can we understand better observations of GRBs? So you can see here some light curve of a GRB, and you can see some quiescent times between subsequent pulses. You can see high variability. It's not entirely understood where this variability comes from, and it's not understood where these quiescent times are coming from. What's their origin? We can also learn about the expansion of the universe if we can have gravitational waves that I will mention later as potentially the best candidates for non-inspired gravitational waves. And conduct cosmological survey by learning about the abundance of supernovae of type 1b, 1c, which are associated with jets, 1c observationally associated with GRBs. And even more interesting, maybe a zoo of powerful explosions, maybe other types of explosions that coming from jets but are not GRBs. Just like these fast blue optical transients that I mentioned before, and I will mention it again later on. So a lot of observational phenomena that we don't fully understand might be connected with this setup of collapsars, and we can study this better. But there is one thing that theoretically is very hard for us to study, and this is this challenge of 7 orders of magnitude in space and time between the black hole and the emission zone. And the way to tackle this problem is to use numerical simulations, specifically general relativistic magnetohydrodynamic simulations where we can evolve both the black hole and the evolution of these highly magnetized jets all the way to the emission zone. And this way we can connect the black hole to the photosphere and maybe address these topics that I mentioned in this slide. So this is what we did. We've been working on this for a couple of years, and using a novel scheme of adaptive mesh refinement in the GPU accelerated code, we managed to not only bridge this vast dynamical scale, but also reach the highest resolutions ever of gamma ray burst or jets in general simulations. And soon enough, we will also have neutrinos, and this will allow us to study these heavy elements that can be produced in collapsar for the first time from first principles. So let me show you some of these results and talk about some implications later on. So this is an example of a collapse we take a star, we let the star just collapse, and the collapse of the star will just form a disk and a jet. These are the properties of the star. So the star is collapsing under its own gravity. And you see here, this is the disk that is on the vertical axis. These are the jets. and the cocoon is in gray. And you can see that the jets are launched from the disk, but the disk is starting to tilt. And this tilt of the disk is something that is seen for the first time, and this is coming from feedback from the cocoon. So what happens is that gas from the cocoon is hitting the disk, transporting angular momentum to the disk. The disk is starting to dance, and the jet is always aligning with the disk because this is where most of the angular momentum of the system is. So the jet is subsequently also dancing. This is something that has never been seen before in jet simulation, GRB simulations, although there have been thousands of GRB simulations. And this highlights the importance of having first principle simulations of jets. It's very different than the first movie, if you remember, that I showed you before.
Is there a black hole?
Yes, there is a black hole that is too small to be seen.
But how are you drawing the black hole?
I start with a black hole.
You start with the black
I assume, yes. So I must say I skip the proton-neutron star phase, which presumably takes, say, 100 milliseconds. And I assume that the structure of the star didn't change much. And actually, when you compare it with proton-neutron star evolution phases, you see that only the core is changing, and it's changing just in the way that we set it up. So
this is a easy jet, or
this is a busy jet, yeah.
and the angular momentum of the black hole is flipping around.
So we explore the angular momentum with different spins that we set in the black hole. This is part of the initial conditions in the system.
Sure, but I'm asking, the jet is reorienting, and how much, but the black hole is more of a flywheel, right? Its angular momentum isn't changing as rapidly.
So most of the angular momentum of the system is in the disk.
Sure.
It's true that in our setup, the black hole is sort of static. So it has a fixed rotation axis. It doesn't evolve with the disk. But because most of the angular momentum is in the disk, it should not make a big difference.
But I guess what I'm asking, for example, simulations of riots that have been done, where the angular momentum direction of the riot is disoriented with respect to that of the black hole, the jet bends in response to the changing angular momentum direction of the plasma around it. Is that what is essentially happening?
I see. Okay, so you're asking about what happens to the jet farther away from.
Well, is the changing direction of the jet due to the bending of the jet interacting with plasma?
Yes, yes, that's a good point. So, in fact, what you see here is that the jet is changing its angle by 30, 40 degrees. These jets would never be able to escape from the star because they don't have enough power considering their wobbling motion. So what happens, in fact, is that this jet, once it's hitting the cocoon, it's deflecting back towards the axis where there is a lower density. So it's naturally gets sort of recollimated by the interaction with the cocoon and is deflected back and start propagating closer to the axis, if this is what you're asking. So the jet, yes, indeed. The initial angle of the jet is not the same angle as with which the jet is breaking out from the star. So it is bending.
Also, as the jet is wobbling, that's limiting its focal length factor.
Correct. Yes, it makes it much harder for the jet to propagate. In fact, it makes the effective opening angle of the jet to be the wobbling angle of the jet. And this, of course, requires much more power and creates can of worms when you get these jets out.
So how far out have you simulated the system of wobbling jet plus cocoon?
Let me show you. Okay, so this is by following the large-scale evolution of the system. So this is exactly the same simulation. This time we just look at the evolution of the jet and the cocoon, and you can see this is the star in blue, so they're already escaping from the star. And you can see that the structure of the jet is very different than what we previously saw. You see these chunks of relativistic material that are interacting through internal shocks. We see the wobbling motion of the jet, and it's not just running along one axis. This structure of jet is essentially a paradigm shift in jet evolution. It's never seen before. And indeed, it makes it much harder for the jet to escape. This is why there are many intermittent phases in the jet. But if the jet is energetic enough, it can make it out.
This deflection mechanism you're talking about must mean that it becomes much less efficient at larger radii, yes? So
right.
how much longer do you actually have to run the engine to get this to get out?
That's a good question that I unfortunately don't have a large enough sample of simulations to give you a sort of like theoretically based answer. In this specific simulation, it was about 2 or 3 times the breakout time of the jet from the star before it evacuates this funnel along the axis.
And these secondary relativistic blobs, they sort of look like blobs you get in jet cluster simulations. Are they moving sort of hydrostatically and they would produce a sort of off-center explosion once they get to the edge? Or because it doesn't look like they could be moving very relativistically like some of these.
Okay, I am not sure how you see it, how fast. I mean, there are.
Well, for example, if they're sort of curled and oval.
Right.
I mean, that can't be very high Lorentz factors.
Right. Yes, I agree. So that's another, of course, imitation of numerical simulations with busy jets. So these blobs, they move at Lorentz factor of between 5 to 10. They do have a little bit more magnetization and entropy to accelerate, but not to hundreds of what we observationally know. So indeed, this is a problem.
So you've been finding numerically some mixing of this material with polymer material.
Yes, it's a very strong one. This is why I mentioned before that we may need the Lorentz factor initially, at least if you trust these simulations of more than 1,000 or so to get to the observationally. Okay. So what can we take physics-wise from these simulations? So as I mentioned, there is really new jet physics here, and one thing we can do is, as I mentioned, to connect jets with observations of stars. So let me give you one example. One example would be that we can infer the black hole spin. How can we do that? I will show later, in the context of binary mergers, that the spin of black hole is in busy jets is directly connected to the power of these jets. And this power of jets, we know observationally, it's constrained observationally very well. And we know to some extent the efficiency of the emission of these jets. So that means that we can constrain the black hole spin. And what we find is that if we start with a high spin, these jets will give you emission that is stronger by 2 orders of magnitude than what observationally we see. So they must be launched from a low spin, slowly spinning black hole, say 0.2 roughly. Even more than this, even if you were to start with a high spin, because the jet is working by extracting angular momentum from the black hole, it would inevitably spin down the black hole to the equilibrium spin, which is the spin that the black hole gains from accreting material from the star and the angular momentum it loses by launching this jet. So we find that it will always reach sort of equilibrium spin of, say, about 0.1. So all these black holes must be very slowly spinning, and unless there is some conspiracy of these collapsar simulations with other type of explosions, it stands to reason that it implies that most, if not all, collapsing stars will form a slowly spinning black hole.
But can you just clarify? Because, of course, the magnetic field is a second parameter. And so,
why it has to be meant
to raise the spin and lower the magnetic.
Right. Okay. So, in order to get the jet out of the ergosphere, you need a magnetohydrodynamic wave to propagate faster than the time or the material that is falling onto the ergosphere. And this is something that is directly connected with the strength of the magnetic flux on the black hole. And when you work out the calculation, what you find, and also in the numerical simulations that we are in, is that if the jet does not reach a magnetically arrested disk, the jet cannot escape from the ergosphere. So this is how we can constrain this efficiency of the magnetic field to be always close to unity, and this leaves us only with the efficiency of the spin. And I will show in this context in binary mergers later on.
So I have a question about going back to the BZ jet, but you said a static black hole, meaning the spin is always along the same axis.
Right.
But the spin, you're now telling us, is being controlled at some level by the accretion onto the
Right.
black hole. You see that in sims.
You're asking in the sense that my simulations are not consistent with the spin down or spin up of the black hole.
Right.
Yeah, so I agree with you. Indeed, the simulations are not consistent with this. This is why, for the first conclusion, we had to run a set of simulations with different spins and see what is the power that you get. This power is independent of spin down or spin up. It's directly
Sure,
the
just
spin.
whatever your actual spin is.
Yes. As for the spin down, this is something that we had to calculate semi-analytically by starting with a simulation, calculating the angular momentum accreted onto the black hole, and work it out in sort of an iterative way.
So then one other question, like, are you allowing the spin of the hole to go flip back and forth or not? In other words, there's the amount of spin and there's also the direction.
Right. No, it's fixed.
It's just fixed.
Yeah.
So the jet tilting around is because of the magnetic field accreting onto the hole. It's in a different direction, or because of the material around it.
The angular momentum is, most of it is in the disk. So
Right.
once the disk is starting to tilt, the black hole is also, not the black, sorry,
Now,
the
the
jet
black hole
will,
you have fixed, but the
Right,
jet
right.
follows the disk.
but the jet will follow the disk.
And there's no Ladford Payne type effect that you see in sims.
There might be, which is something you are more likely to see when you reach lower spins, because then the jet is less energetic.
Sure.
When the jet is launched from black holes of 0.1 or more,
It's
it's
just going to dominate.
exactly.
So, the lines of questioning got me confused from your very clear explanation in the beginning. And that was that the jet is perpendicular to the disk wobbles, and the wobbling had to do with the instantaneous or accumulated accretion that was going on from the cocoon.
Right.
So that means that you must be able to learn something about the angular momentum distribution in the star that is, as successive pieces of the star fall on the black hole. It doesn't seem to be all lined up.
So you're saying observationally, if we see this type of behavior, we can infer or at least say something about the angular momentum distribution in the star.
Yeah, it seems more chaotic than just.
Right. So we were looking for some characteristic timescales over which it processes or something like this, which of course would be interesting to compare with observations. Unfortunately, we don't have a large set of simulations where we can self-consistently address these questions, hopefully in the near future. We haven't found any periodicity in the way that the jet is wobbling, which makes it much harder because everything there is very stochastic. But I agree with you that this is one of the interesting avenues to explore in the context of inferring the, probably, I would say arguably the most enigmatic property of collapsing stars is their angular momentum. So yeah, we are thinking, but I think we're not at this point yet.
Just to be clear, the simulation you ran, you started with a rotating star aligned with an initial black hole, and something about the turbulence in the disk broke the symmetry, and all the wobbling that we're seeing is the result of broken symmetry, not collapse of different shells.
Yes.
Different elements.
Exactly. Okay, kicks is also something we see. We haven't published this, this is preliminary, but we do find that the jets statistically have 10% difference in the linear momentum, the jet and the counter jet. This can induce kicks of hundreds of kilometers per second into the black hole. This is something that is also interesting to study, of course, and we're on it, but this is again preliminary. And the last thing I would like to say about jets in this the simulations is what you already mentioned multiple times, and this is the wobbling motion. I think it has at least two important implications. The first of which is if the jet is wobbling, it means that we're missing less of them because they cover a larger solid angle on the sky, And that means that when we try to infer the intrinsic rate of GRBs from what we actually observe, it must be lower by up to an order of magnitude compared to what is inferred from an axisymmetric jet that is propagating along just one axis. This, of course, changes the rates to something that makes it much less promising for GRBs jets.
You mean we're missing less of the successful breakups?
Yes.
But there's more.
I'm not arguing anything about jets that we cannot see. I'm arguing only that the jets that we can actually see are more rare in the universe. In fact, we can talk about it, but this may be an indication that there are more jets that are choked. Quiescent times, remember I mentioned this mystery that we don't understand quiescent times. So here is a natural explanation that you get for free from these simulations. The jet is wobbling, it means that we see different jet elements intermittently, so we get quiescent times quite naturally.
So you also have a prediction about how the spectrum would change as it goes out of your line of sight.
In principle, yes.
Yeah.
We haven't run such calculations. Okay, let me talk a little bit about other types of messengers. So, what about gravitational waves? I mentioned that we may have gravitational waves from collapsars, and the reason is that collapsars, they are hosts to the maybe two most luminous events in the universe, GRBs and 1BC supernovae, broad line. F-bots that I mentioned before might also be part of this story, and therefore they are ultimate candidates for producing gravitational waves because they have a lot of energy there. All we need is enough energy in the quadrupole moment of gravitational waves to get something that we could detect later. So when we look into the two types of sources, the first of which is the supernova, the problem with supernova is that the quadrupole of the supernova is something that is going to be very weak, and this is because the spherical explosion is spherical. So although it's not entirely spherical, it's spherical enough so the emission would be very weak. So you can see here calculations by David Radice that shows that at about 10 kiloparsec it's marginally detectable. So we can see supernova through gravitational waves maybe in our galaxy, not on extragalactic scales, and that implies that maybe once in a century or so with current facilities we will be able to detect this. As for GRBs, the situation is much better. GRBs obviously are asymmetric. The problem with GRBs is that the perturbation that they induce in space-time is roughly proportional to the working time of the jets, which is observationally about 30 seconds. This corresponds to frequency of a few tenths of millihertz, which is way below the detection bands of LIGO. It might be detected in future space-based interferometers. So you can see the jet emission in yellow. You can see the LIGO that might detect it in the future, but it seems unlikely that LIGO will be able to detect gravitational waves from the jets, although the quadrupole moment is rather substantial.
So what's specifically the component that is associated with the quadrupole?
Components
Of the explosion that's producing the quadrupole.
So the jet itself is producing the gravitational waves, and the quadrupole is a matter of viewing angle. So if you are looking at the jet head-on, assuming it's an axisymmetric jet and so forth, you will not have a substantial quadrupole moment. If you're looking off-axis, then the propagation of the jet in space will just produce gravitational waves. And of course, these are all analytic calculations, so you should take them with a grain of salt, because as we saw, the jet is not evolving in such.
But at what rate is this emission concentrated?
So the frequency would correspond to the longer between the duration of the jet and the acceleration timescale. This is basically the time over which you compute space-time. So here, the longer between the two in the case of long gamma ray bursts would be the duration of the burst, which is roughly 30 seconds. So you can think of one element in space-time that is perturbed over the duration over which the jet passes through this element. So it will sort of wobble in space-time for 30 seconds before it will relax. That's at least the way I think about it. Now, another component to think about that we already saw before is this cocoon. The reason why cocoons could be interesting is because, first of all, their shape is naturally asymmetric, so they can give rise to a substantial quadrupole moment. They have better frequencies in the sense that they evolve over much shorter timescales compared to the jets. So they might end up in the frequency bands that LIGO is sensitive to. Their energy is at least as much as that of the GRB. If the jet wobbles, it actually implies that the cocoon has a little bit more energy than the jet. And as we saw, it's also a promising electromagnetic source. So it can be, for itself, a promising multi-messenger source. So what we did is we ran, again, another simulation with very high temporal resolution to resolve high frequencies. And what you will see here, hopefully the sound works, sonification shows the gravitation, or reads the gravitational wave frequency, and the picture shows the gravitational wave density. It's very but the idea is that you can see the jet that is generating gravitational waves, but the newly freshed shocked material by the jet that you can see here is mostly the cocoon. And this is a strong source of gravitational waves that's not emitting in sub-hertz frequencies, but in higher frequencies. So here is how it would look. So when we're on axis, the emission will be quasi-isotropic, so it will be similar to supernovae. It will be very hard to detect it, but when we're off axis, the emission will be much stronger, and this is how it would look. So off axis would be 1 or 2 orders of magnitude stronger than the on axis, or this is also similar to supernovae. So cocoons are much more prominent than supernovae as gravitational wave sources. The problem is that cocoons are also more rare than supernovae, but overall the rates of cocoons that are detectable by gravitational waves is likely to be larger than that of supernovae. So it peaks at about 100 Hertz. It's the most promising non-inspiral gravitational waves in LIGO, and the big plus is that we can detect electromagnetic emission either from the stock or from the cocoon itself, and then go back and look for this in the data because we don't have good templates for finding these cocoons.
What detection distance are you going? 100 megaparsecs?
100 megaparsecs.
This is 100 megaparsec, but this is assuming essentially SNR of 1, which is unrealistic. So if we go to SNR of 30, which is more realistic, maybe with a little bit of luck, then it gets with 04 or advanced LIGO to be about 10 megaparsec or 20 megaparsec. So it's most likely to be something that we can detect in Cosmic Explorer or future and less.
The range won't be that high.
Right. We need to be extremely lucky in 05. I think about 10% for detection of cocoon gravitational waves in 05, but several events in Cosmic Explorer.
How do you constrain the explosion time for the EM cells?
I can't. The simulation is too expensive for this. I have to just feed it observationally with GRBs.
But practically, if we wanted to go back and search, we would have to figure this out, yes.
Oh, you're asking about the delay time to be electromagnetic. Yeah, I don't have a good answer. I mean, people have worked on this, of course. You probably have to run it for a few hours. That's the uncertainty that you have. Yeah, that's true.
But you only have a few hours uncertainty if you had a very extended stellar envelope to get through, right? If you have a compact star.
Assuming Wolf-Rayet. I agree that if it's an extended envelope, it's much trickier. Although I should mention that by the time we're level 5, we'll also have ultrasat. So hopefully we'll have some shock breakout emission, which will a little bit narrow down the window. But of course, this is challenging. So it depends on the projector, it depends on the observations. Okay, how much time do I have? Not much. So let me just share with you my recent work that is a different type of system and perhaps unknown cataclysmic events. So I want to talk a little bit about FBOTs and why cocoons are excellent candidates for explaining the entire observables of FBOTs, but I think that I would have to skip it just so I will have time to go over what I mentioned before, which is the origin of a new class of GRBs. So you all know that there are long and short gamma ray bursts by now for sure. But apparently there is another class of GRBs that has been suspected for long, but now we know we had a smoking gun of kilonova with long gamma ray bursts. So we know that we have long gamma ray bursts emerging from compact binary mergers. And this is surprising because I just mentioned in the beginning of the talk that short gamma ray bursts were considered to be associated with binary mergers because the typical accretion timescale is about 1 second. And now, all of a sudden, we have 10-second bursts from compact binary mergers, followed by a softer extended emission. And the question is whether they come from compact binary mergers, because we have kilonova, or maybe it's something else. So what we did is that we said, let's see how we can get long bursts by understanding what powers the jet and whether we can constrain these quantities. So there are really 3 quantities that we need to know once we consider the jet launching. The first is the mass accretion rate. So this is how much mass or how much power we have available to launch the jet. And then we have the efficiency of the spin. The faster the black hole spins, as I mentioned, the more energy we can use from the rotation energy of the black hole to power the jet, and the field efficiency. The stronger the magnetic field, the stronger the point flux. And this is what Chris mentioned before about the uncertainty or the degeneracy between the spin efficiency and the field efficiency. We need to know one in order to constrain the other. So once we know these 3 quantities, we understand very well the jets. So let's start with something very convenient. The spin of post mergers is always close to 1. The efficiency is always close to 1. Binary neutron star mergers will always have post merger spin of about 0.7, 0.8. Black hole neutron star mergers, the black hole will be spun up, and if it starts very low or non-spinning, we will have no electromagnetic counterpart because there will be no formation of a disk because there is not enough angular momentum. So this is why when we see jets, it's safe to assume that the spin is up to a factor of 2, or the efficiency of the spin is about 1. And this leaves us with only 2 quantities, this and this. And then we can just draw it as evolution in time. So we can look at m dot, which is the mass accretion rate. The mass accretion rate is following a power law. Unlike collapsars, where the disk got more mass from the collapsing envelope, in binary mergers, the disk is just depleted over time gradually. And what we see in all numerical simulations, not just of our group, but also of other groups, that m dot is always falls close to t to the minus 2. This is after about a few tenths of milliseconds, which is the characteristic timescale after which it converges to a power law. This can depend slightly on the physics. If you were to include alpha ray combination or other types of physics, it can change the slope by a little bit, but not by too much. And that implies, first of all, that there is no really timescale that is relevant to GRBs, because GRBs happen on much longer timescale than a few tenths of milliseconds. So this argument of timescale in binary mergers seems to be a little bit irrelevant. And then the other quantity, which is the efficiency of the magnetic field, is something we can constrain from this. So this is the power of the jet, which scales with the magnetic flux threading the black hole. Now, the magnetic flux threading the black hole is all the flux that was advected from the disk to the black hole. In post-merger disks, the disk is always very small. It's a few, maybe 30 gravitational radii. That means that the magnetic flux is advected onto the black hole within no time. So that leaves the flux on the black hole nearly constant, and that implies that if we know that m dot follows as t to the minus 2, this must rise as t squared. So the efficiency of the magnetic field goes as t squared until it reaches unity. At this point, the disk becomes magnetically arrested. This is when the magnetic field becomes dynamically important, and then it remains saturated at unity forever.
But as m dot drops, that flux has to start expanding back up.
At this point,
Yes.
I agree. At
And
this
you're
point,
and you're taking that into account.
yeah, so as you can see here, Pj is the product of the two, so it will be constant, and once it becomes met, indeed flux will start diffuse out or leak out from the black hole. And this is great because this is exactly what we see observationally. The prompt emission of GRBs, although it's highly variable, shows no trend in time as if it goes up or down. Okay, on average, it's roughly constant, and this follows by extended emission that the fit to which is about t to the minus 2. So if this is true, it means that we understand the basic underlying physics of post-merger disks and prompt and extended emission in GRBs. Now,
How many events now have the t to the minus 2 extended emission?
it depends what you're asking. So some people argue that up to 75% of GRBs have extended emission. Some people argue that it's as little as few as 20%, but it's definitely not something very rare. So there are many
But the
companies.
ones where you see the extended emission, it always goes like t to the minus 2.
No, so of course there is some variance when you look at the distribution, but the best fit that I know that all the studies I saw, and that they always find t to the minus 2. But this variance is going all the way to t to the minus 3 or so.
It's a strong.
Right. So, okay, how do we connect it with duration? So, obviously, if we start with a stronger field, we reach saturation earlier, the jet will produce a shorter prompt, followed by extended emission. So that means that we can play with this for the duration, and this is already good news, but of course, we also have the normalization of m dot. So if the disk is more massive, we also have to take this into account. So if we go to numerical simulations, we took 10 different simulations of black hole neutron submergers and binary neutron submergers, all of which yielded the disk of 0.1 solar mass. And these are the gray lines, and we fitted it. And what you see here is t to the minus 2. This is the fit, this is m dot. Now, if you have 100% efficiency, this would also be the power. But as we saw, the power would depend on the initial field. So if you start with a very strong field, then you will reach saturation early on. This will be roughly the characteristic timescale of a short GRB, fraction of a second, but this will be 2 orders of magnitude more luminous than short GRBs. That implies that in order to get the right luminosity, we have to start with a much weaker field, which is more realistic too. And then we get the right luminosity, but it will reach a saturation point, which is the duration of the prompt emission, only after about 10 seconds, which is the duration of the long gamma ray burst. So that shows you that not only do massive disks produce or can produce long gamma ray bursts, they inevitably produce long gamma ray bursts because this can be ruled out observationally. So massive disks produce long gamma ray bursts, whether these are the bursts that we saw or not, of course, we cannot know, but it seems likely. And then we can connect it with the underlying physics of the merger. So long gamma ray bursts are, if they are produced by massive disks emerge from unequal unequal binary mass, binary neutron stars. So if we have a binary neutron star with a mass ratio of about 1.6, we expect a massive disk which will produce a long GRB. Similar in black hole neutron star mergers with mild mass ratio and high spin, we can also get massive disks that will produce long GRBs. As for short GRBs, they can be produced either by equal mass ratio binary neutron stars or from other types of black hole neutron star mergers. I would just mention that we need to be careful. Most binary mergers, if you judge by the binary neutron star merger population in the galaxy, have this total mass, which expects to give a hypermassive neutron star before a black hole. This will change this picture. And also we know that compact binary GLBs are likely to have some bimodal distribution rather than a continuous one. And in this picture, you see a continuous distribution. So alternatively, I would just mention that it's possible that hypermassive neutron stars are the engine for short GLBs, and black holes are the engine for long GLBs. And there are a few ways where how we can study which of these central engines indeed power the short GLBs, but long GLBs are most likely produced by black holes with massive disks, and this is how it will look. So this is the light curve of this prototype of long GLB. It starts with a precursor flare that can either come from some stochastic busy jet or hypermassive neutron star flare. If it's a short GLB, it can be produced by either a non-mad light disk or hypermassive neutron star. But in the case of a long GLB, it must be, or seems to be at least, massive disk before it enters the magnetically arrested disk. And once it enters the magnetically arrested disk, it will follow T to the -2 to produce the extended emission. So I'll leave my just because I'm running 3 minutes late, I just leave my questions. Happy to take questions. Thank you for your attention.
So you're going to get very different after those properties. Your primary merger one here is the plots. Forming from the wolf there. What can you predict about the differences in afterglow?
For a wobbling jet?
No, sorry, for the binary merger induced long GRB versus a collapsar long GRB.
It's a good question.
This extended wind in the case of the wolf rays.
Right. So I haven't studied the hydrodynamic evolution of these jets over large timescales. It does seem like the wobbling motion, for instance, is something that is more prominent when you consider long GRBs because of the stronger interaction with the stellar envelope compared to the ejecta. If indeed wobbling is something that we see in long GRBs and we don't see as much in short GRBs, this should have some manifestation in the jet break, I guess, in the afterglow when we observe it. But all of these things are things that need to be studied. I don't know if you were asking me how would look the afterglow emission from a wobbling jet. I don't know.
The wobbling, I mean, maybe it's always present, but I would sort of set that to the side and saying you've got a jet of a certain energy produced in the binary merger with a very brief neutron-rich outflow preceding the formation of the jet versus a jet of comparable duration plowing through a dense stellar envelope and then encountering an extended stellar wind. So that's a rather different environment.
I agree.
You have a nice argument about the duration of the jet.
I don't know if, top of my head, I cannot think of anything to distinguish between long GRBs from that are coming with an exploding envelope and with our process ejecta. I'm not sure if there is a way I can think of to.
But actually, let me just take a step back. So for the collapsar case, the argument you just given with the magnetically arrested disk and the gradually diluting flux would still hold, of course.
Right.
So it doesn't necessarily only apply that to the merger case.
Well, isn't it very different because you have a fresh supply of material with flux?
Well, you could, but this is something actually we just said at lunch. I mean, there's the issue that the wind from the disk could be blowing up the star quickly. So basically, then you're dealing with whatever disk you have there. And like in the binary merger case, it'll be gradually spreading outward and diluting.
I'm not sure exactly what quantity you're referring to that you think is different between binary mergers and collapsars.
Well,
the accretion rate or the efficiency
well,
of
Chris was just referencing the fact that in the absence of the complete explosion, there'll still be stuff falling down onto the disk.
Yeah.
And that would certainly change the duration. That's sort of the
In
picture.
collapsars.
Yeah, that's the most popular picture for the duration that people have, right?
Right.
But if in fact, the star just basically blows up quickly, and then you're just left with the passively spreading disk, then there's a strong similarity in the two cases.
Yeah, if the supernova, if you have a core bounce that is for some reason, well, presumably you have the explosion you're saying that takes place much before the jet was launched.
Well,
Otherwise,
again, the time to collapse 3 solar masses is quite brief. It's like a second.
I agree,
So what could be left.
but you still have the entire envelope.
So you still have the issue of how much angular momentum is in the envelope and how much time it takes to build up to this. Right? That's a free parameter. If you did have a prompt formation of the disk, then you would be in a similar situation, but we don't know that. I guess that might be a fair way of summarizing.
If somehow you unbound the entire envelope, yes.
Well, once you form the disk, I think it's a good idea.
You say that the jet will unbind the entire envelope. I don't know. I mean, I agree to some extent because you still have bound material in the cocoon, which has enough mass to power the jet for some time.
I see. So it's a more delicate question.
Yes, it's not just free fall from the outer envelope that I agree that will be unbound. You also have bound material circling around stochastically with the cocoon.
But then to understand what happens to that, one really needs to model the disk outflow in more detail.
I agree with this, yes.
But your sims can do that.
They can do that within the limitations of stochastic behavior.
Well,
But yes,
sure.
in general, yes, yes, this is something that can be explored numerically.
Any more questions? Any questions online?
We had a lot of questions already.
Okay, I guess not. Then let's thank our speaker.